Alright, in this video we look at section 5.1 and we consider the Riemann sum idea, and we try to transition to a larger number of rectangles, and to do that we begin trying to be more careful and look for patterns in the mathematics that we're doing. Okay, so in this case we're noticing that we have the function f of x is equal to 2x plus 1, okay, and we're on the interval I going from 0 to 4, and we would like to find the area under this graph f of x equals 2x plus 1 on the interval I equals 0 to 4. Okay, and we're going to do that by trying to build up a pattern and start from a small number of rectangles. In this case, n is equal to 2, and implies that delta x is b minus a divided by n, which is equal to 2. So we have two rectangles in this case. We're going to evaluate the function, okay, on the right point of each subinterval, which is 0 to 2, and then from 2 to 4, those are our two subintervals. And we're going to evaluate at the right endpoint, because that is going to be just a good place to start when we're looking for patterns. Okay, so here's what we need to evaluate. Now the trick here is that adding up these rectangles is going to be evaluating the function at the right endpoint. The first right endpoint is 2, and then we're going to multiply by the width of that rectangle, which is 2. Evaluate the function at 4, which is the second right endpoint, and then multiply by the width of that rectangle, which is also 2. And this will give us an approximate area for the area under the curve. But since 2 is in both locations, the width of the rectangle is both 2, we can factor out that 2, and then we can just evaluate the function at 2 and the function evaluated at 4. Now, again, in this video, we're trying to notice particular patterns. So notice that the function evaluated at 2 is the same thing as 0 plus 2, and 4 is the same thing as 0 plus 4. Okay? And the reason we're writing that is because I want to point out a couple of things, that this 2 here is our delta x value. That was something we knew from the beginning as soon as we had determined our n value and as soon as we knew our interval. Okay, so delta x will be an important quantity to keep a lookout for. Notice that this 0, I have brought this into the game because we were trying to find the area under this function from 0 to 4. 0 is the left endpoint. It's the leftmost part of the interval that we are looking at, and we end at 4 because that is our right endpoint. Okay. Now if we continue on with this process, notice that the function at 0 plus 2, 2 is the same thing as 2 multiplied by 1, and 4 is the same thing as 0 plus 4, but 4 is the same thing as 2 multiplied by 2. And then we're going to have the multiplying by 2, which I need to, let's see if I can bring this over a little bit. Sorry, so I have more room to write. I don't know why this part's so complicated. Alright, well there's a 2 over here. Alright, so what we can see is that we have the function evaluated at 0 plus 2 was our delta x, multiplied by 1, the first rectangle, and then the function evaluated at 0 plus this 2 is delta x again, and this 2 is because there is a second rectangle. And then we multiply by the width of the rectangle, which is 2. So if we're looking for a pattern here, we're noticing that we have delta x in several locations, right? There's delta x. And then this 1 and this 2 change because we're going from n is equal to 1 up to n is equal to 2. We had 1 and then 2 rectangles. Okay? So then you could evaluate this to be the function evaluated at 2 plus the function evaluated at 4 times 2. Here's the function evaluated at 2. Here's the function evaluated at 4. And then the delta x is equal to 2. So if you wanted to just evaluate those numbers now, the function at 2 would be 5. The function evaluated at 4 is 9. And then we get 14 times 2 is 28. Okay, and that was the n is equal to 2 case for the approximate area. Okay, so as we move to a larger number of rectangles, I want to call your attention to this short, what we're going to be looking for a pattern. Okay, so let's go to our next example. The n is equal to 4, and we'll see if we can see what happens. Okay, so here we're seeing the same problem. Okay, we're seeing that the function f of x is 2x plus 1. Okay, we're still on the same interval, I going from 0 to 4. And now we're going to choose n is equal to 4 rectangles, which means that delta x is going to be equal to 1. So if delta x is equal to 1, here are the 4 subintervals that we're looking at, from 1 to 2, 2 to 3, I'm sorry, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And again, if we take the right endpoints of each of these intervals and evaluate the function at those right endpoints, okay, and then draw rectangles across from there, we now have 4 rectangles. And we can then see that the approximate area is going to be the function evaluated at 1, the function evaluated at 2, the function evaluated at 3, and then the function evaluated at 4. And all that would be multiplied by 1, the width of each rectangle. Delta x is equal to 1. So again, we're in the business of looking for patterns. Notice that the function evaluated at 1 is the same thing as the function evaluated at 0 plus 1 times 1. Okay. 2, the function evaluated at 2 is the function evaluated at 0 plus 1 times 2. The function evaluated at 3 is the function evaluated at 0 plus 3 times 1. The function evaluated at 4 is 0 plus 4 times 1. And then we multiply by 1. So I'm hoping that we're seeing the pattern here, that this 1 here on the very outside, that is our delta x value. Okay, we are seeing this 1, this 1, this 1, and this 1. Again, that is the delta x value. And then we're seeing that we're counting 1, 2, 3, and 4 because our number of rectangles is going 1 to 2 to 3 to 4. We're ending at 4 rectangles. And there is 1, 2, 3. Alright, so we'll continue with the video. There we go. And so now we can see that what we have here is the pattern, that there is a function value. We're evaluating at 0 plus some number times delta x, okay, and then we are multiplying by delta x. Each of these numbers is getting multiplied by delta x. And because this number 1 changes from 1 to 2 to 3 to 4, we can say that that is just a counting number, I goes from 1 to 2 to 3 to 4, and because we're adding up all these numbers, we can put this notation here called sigma notation, that I goes from 1 up to the total number of rectangles, which in this case is 4. Okay, so this notation is meant to represent, right, this is called sigma notation, and it represents when I is equal to 1, you'll put a 1 here for I, And because delta x, we know in this problem, is equal to 1, when I is equal to 1, you'll get 0 plus 1 times 1. That's I is equal to 1. And when you go to I is equal to 2, this sigma notation, this Greek letter sigma, means that you put a plus sign in between them, and then you move to I is equal to 2. When I is equal to 2, you'll get 0 plus 2 times 1. 1 is equal to delta x. Put a plus sign, move I is equal to 3. 0 plus 3 times 1. And then finally, we'll get to I is equal to 4. 0 plus 4 times 1. And then all of that is going to need to get multiplied by delta x. So the advantage of this sigma notation is that it's available to us in Desmos if you click the little keyboard down here in the bottom. Alright, so in Desmos, clicking the little keyboard will bring up a function that you can put in, and one of those functions is the little sigma notation under miscellaneous. Let's go to a new 2x plus 1, so we put our function, let's go to a new line, then we can insert this function, sigma. And the advantage is that if you have done this sigma notation in writing, you can just type in what you have written by hand. So I is going from equal to 1, right? That's the number of counters of rectangles, and we've gone up to 4 rectangles. If you have the function, you can say that it's 0, the left endpoint, plus I multiplying by delta x. Since we had 4 rectangles, 4 divided by 4 is equal to 1, so delta x is 1, and then you multiply by 1, and we can see that the answer for this sum of 4 rectangles is 24. Now the advantage of this is that when you go to a larger number of rectangles, so let's say perhaps n is equal to 16, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 rectangles. So when n is 16, all you need is delta x, which is 4 divided by 16, which is equal to a fourth. Okay? We know that the interval goes from 0 to 4, so we know that we're going to have the summation. The number of rectangles is going to go from 1 up to 16. We're going to have the function evaluated at the left endpoint 0, so 0 is the left interval, and because we're doing right endpoints, we need to add on a little bit. We're going to add on I rectangles, I going from 1 to 16. We're going to multiply by delta x, which is 1/4, and then we need to multiply by the width of those rectangles, which is delta x. So the general notation that we're seeing here is I going from 1 up to some number of rectangles you pick, the function evaluated at a, which is the left endpoint of the interval, plus I delta x. So when you do the a plus I delta x, that means that you're doing the right endpoint problem. Okay, and then you're going to multiply that by delta x. So the advantage of this notation in the Desmos is that you can just simply change a couple of numbers here, go up to 16, 0 plus I times 1/4, and then if you multiply by a fourth, delta x, we can see here that this is where the 21 comes in. Okay. So we can see that when n goes to 16 rectangles, we get 21, which is closer to the actual area. And for example, the cool thing here is that if you wanted to use like 500 rectangles, you could say that I would go from 1 to 500. Delta x would be 4 divided by 500. The interval was with 4 divided by 500, so delta x is 4 divided by 500. And we can see here that when n goes to 500, the approximate area would be 20.032. right? Which is getting much, much closer to the exact answer of 20. So in the next video, we'll look at taking this limit with mathematics going to infinity.